I feel like the lectures we gave prior to Carnival were kind of like core complexity theory. You know, kind of complexity theory from its inception in the mid-60s up to about the end of the 80s. You know, like the basics of space, time, randomness. We got it done, so that's good. So now we have 4 lectures left. And, you know, I want to give you a bit of a glimpse past the 80s into the, I was going to say into the future of complexity, but it's really like still the past, but it's getting closer to the future. So, right, so today, let me give you the plan for the rest of the lectures. Well, today we're going to talk about interactive proofs, as it says on the board. Probably you've seen these before somewhat in 251, but we'll do them a little bit more now that we're more up to speed on complexity. And this stuff is from like the early 90s. OK. That's before. Then on Thursday, let's see. On Thursday, we're going to talk about some aspects of beyond sort of worst case analysis of problems. So we're going to sort of talk about average case hardness a little bit, and hardness of approximation, and about something called Feiget's hypothesis, which, like the exponential time hypothesis, is a hypothesis that's stronger than p does not equal np. But if you assume it, then you can prove some interesting things. This stuff is from like the early 2000s, I guess. So maybe you were alive then. And then the next Tuesday, we're going to talk about hardness within P. OK, so you know, in real life, having an algorithm that runs in n-cubed time is not so great, even though it's in polynomial time. And perhaps we can use the techniques and ideas of complexity theory to show that some problems really, let's say, require n-cubed time and cannot be done in n to the 2.9 time. So this topic is actually it's a pretty natural topic, but it didn't really come up until like the mid-2010s, so like basically now. And then the last class, which I guess is also Thursday, but well, we're going to talk a little bit about like why is P versus NP kind of hard to prove. So I mean, P versus NP is funny. It's like, you know, people are so frustrated by the inability to prove it, they started proving theorems about why it's hard to prove it, because they had nothing else they could do. And there's quite some interesting work along these lines recently, but we're going to actually, so now we're actually going to go back in time. This is from 1975. There's more modern takes on this thorny question that we'll get to. Well, we won't get to, but we'll at least get started with this. So I'm probably going to like shoot myself in the foot for saying this, because it'll probably impact our already stellar attendance. But these things will not be on the final or even on the homework. And this one I have not decided. I guess maybe some aspects of it could be. So you should still come to class, though. It's going to be great. These are very exciting topics. I'll tell you all about them. You'll get hyped for complexity. I'll tell you the gossip of complexity theory, who's dating who, everything like that. It's going to be great. So you should definitely attend. OK. So today, interactive proof. So yeah, you may remember this somewhat from 251, but I'll remind you, and we'll go over some more aspects of it. So I want to actually sort of talk about proof systems. And what does this mean? Well, systems for proving statements by which, you know, a person can kind of become convinced of mathematical statements. And all our statements are going to be of the form, this string is in this language. OK? And we have a proof system that we've talked about a lot in this class. It's the one that sort of forms the definition of NP. And we'll talk about this exact proof system now, but it's common when you start talking about proof systems to kind of make it a little bit anthropomorphized, where like you have some characters, namely the verifier v, which will be some kind of polynomial time Turing machine, but you can think of it as some character, and a prover, which we'll call p, although that's we use p to stand for a lot of things, but p will stand for prover in this context. And unlike the verifier, the prover is imagined to be some kind of like all-powerful like entity that can like do as much computation as it wants. You know, infinite computation. It can do anything. It's not constrained. It's just the verifier who's kind of trying to check the proof is constrained. And proof systems all sort of started the same way. Like you have some statement that they're trying to prove. This is like an eyeball, apparently. They're both like looking at this statement that like X is claimed to be in the language L. And the situation is that the prover is trying to prove this statement to the verifier. And you should always imagine the prover is trying to prove the statement to the verifier regardless of whether or not it's actually true. OK? And so we usually divide our mental model into two cases. Like when it's actually a true statement, we're imagining like the prover is like this helpful, omnipotent character that like is providing good evidence that the verifier will accept. And when the statement is not true, we imagine the prover is like a cheating prover that's still trying to like trick the verifier into thinking that the statement is true, even though it's false. OK, so from the verifier's point of view, it's like kind of a trust, but well, it's not really trust, but verify. Anyway, like the verifier is like skeptical of the prover's statements. But if the prover manages to, you know, give the verifier some evidence that it accepts, then it can become happy. So OK, the basic proof system that we've talked about before, and it's kind of the proof system you get when you like crack open a math textbook, and it's like theorem proof, is basically there's some message from the prover over to the verifier, call it y. And you know, this complexity theory, we always imagine that the length of the message y is polynomially bounded in the length of x, because the verifier, you know, only has so much time to read the message. And in the basic system, this is supposed to be some kind of proof or certificate or something that can like help the verifier become convinced that x is in L. So you know, what we imagine then in the most basic setup is that v, you know, operates on x in this proof or certificate y. And let's see, it does a polynomial time computation. Right, like it's actually a, you know, Turing machine. And then it accepts or rejects. And this is supposed to be it giving its opinion on whether or not it thinks this statement's true. And in this basic proof system, we require the following two properties, that if x is in the language, then there is some message or proof or certificate that the prover can send, such that the verifier will accept. OK, so like in the good case, if the statement is true, the prover can send some helpful message that will make the verifier accept. And if it's not in the language, and so we have a cheating prover, then whatever this cheating prover sends over, y, the verifier will reject. OK, this is like the system you have in mind if you're like reading a math textbook, or you're like a TA grading somebody's homework. Like you just get this, you know what the statement of the problem is, and then the student writes down some answer, and you know it's untrustworthy potentially, so you check it, okay, and you either become convinced that they prove the theorem or not. All right, so you know, once you develop the notion of a proof system, and we're going to develop other notions in a second, you can ask, you know, which languages have such a proof system. And for this particular proof system, the language is L with, you know, such a proof system are those in NP. OK, so it's exactly NP that we've defined here. Great. OK, so far so good. That's from the 60s and 70s. And OK, so let's make it a bit more interesting, as befits the name of the lecture. So in like early 80s, in like a paper that was rejected from publication a couple times, you know, Turing Award winners Goldwasser, Macaulay, and Rakoff, you know, they suggested the idea of interactive proofs. I mean, they said, you know, here we are like in a classroom when, you know, I try to prove a theorem to you. Ideally, I don't just like write it on the board and you like check it or not. You know, we can interact, right? You can ask me questions and so forth in our limited polynomial time. And in the human world, this seems to help people verify statements. So could it help in complexity theory? So the setup in interactive proofs, I don't know why I put the colon there, anyway, is you allow the prover and the verifier to talk. And I'm not going to write down a definition with Turing machines and stuff because it's annoying. It'll be clear what it means. But if you want to see a definition with Turing machines, you can look in the textbook. Right, so in interactive proofs, it starts out like this. And they have messages. So the prover, who's all powerful based on the statement trying to prove, sends some message, which is just like a string of at most polynomial length. And then based on that, the verifier can send a message back to the prover. You can think of that as asking a question. And then the prover may send a message back to the verifier. You may think of that as giving an answer. And this can go on. And let's say it ends like this with message number k. It sort of only makes sense to have the prover send the last message because, well, the verifier is going to accept or reject at the end. OK, and this could model some interaction between them. And we're going to always assume that everything should be polynomial. So the length of all these messages is polynomial in the length of x. And k, the number of, so these k is the number of rounds of interaction. So back in NP, we just had 1 round. And we could let this even also be as large as polynomial in n if we wanted. OK. And so at the end, after they exchange the messages, this is going to be the same. The v will do a polynomial time computation. Will actually involve all the messages as well. The v will do some polynomial time computation based on everything that it saw. And then we'll have the same kind of conditions. So if x is in the language, there should be prover message sequence. OK, so there should be some way for the prover to send back responses such that the verifier will accept in the end. Let me just write that. And when x is not in the language, it should be that for all prover responses to the questions, the verifier should reject. OK, so this kind of proof system would model a proof system where the prover and the verifier are allowed to interact. Now, I don't know why I put this in the colon here. I guess they introduced interactive proofs. Anyway, there's a sort of sad fact about this scenario, which is that the kind of languages that have this kind of proof system is just NP again. So let me just say, well, I can just say that this is still exactly true. The languages L, which have such a proof system, is still exactly just NP. That looks a little disappointing because nothing happened. And the reason is it's like you should imagine that the prover is somebody that's taught a course 1,000 times and maybe also is teaching it to kindergartners. Because, well, the key to this, the reason that this is true is it heavily relies on the fact that V is deterministic. OK, so far I didn't explicitly write it, but if I don't write it, then you can imagine this is a deterministic Turing machine. And deterministic Turing machine, it's I know exactly what questions you're going to ask. So I know if I'm the prover, let's say, and we're staring at this x and L, and V is just some fixed deterministic Turing machine, then the prover can send some first message, but it knows exactly what V is going to do. V is deterministic, so it knows exactly the question that the verifier is going to ask in the next round. And if it sends back M3, then it'll know exactly the question the verifier will send in the next round. Okay? And therefore, the prover can say hey, let's cut to the chase. Here's all the messages that I would send, plus all the messages that you would send. And just verifier, I'll send everything to you right at the beginning. And you can just check for yourself, oh, yeah, I would have asked that. And then, oh, yeah, I would have asked that had you given me that response. And oh, yeah, I would have asked that if you give me the response. And then like the verifier can just like verify all that stuff and cut to the polynomial time check at the end. OK, so somehow, when the verifier is deterministic, which is what we naively assumed, it doesn't really help. And when I say help here, what we're trying to do and what we're trying to imagine in this lecture is like more expansive notions of proof systems, which may allow us to have a convincing proof system for problems outside NP even. Okay, that's what sort of the interest is here. And this did not work. You know, any language for which you can have a proof system, interactive proof system like this, is still going to be an NP, because it can be converted to one where the prover just sends like one big message at the beginning, which contains all the interaction they would have had. Any question about that? OK, so it looked good. And as you can tell from the fact that I emphasize the word deterministic a lot, things change if you allow V to be randomized. And this was like this was really like the magic of this paper, to like notice that like the combination of interaction and randomness really changed something. Okay? So you know, it showed that in order for this like teaching format to be really powerful, like it's important that like the students be kind of unpredictable. OK, so now we're going to imagine, the key is, I'll put the colon back, V can be randomized. And what's good about that? Well, at a basic level is, so the prover sends some information to the verifier. And now the verifier might ask some kind of random question back to P. And before, the prover like knew exactly there was one question that V would send back if it sent this message. And now there's at least exponentially many potential M2s that V could send, right? I mean, if it's, you can use n coin flips, it could make up like 2 to the n different questions to send back. And it's not like the prover can like preemptively send across the answers to all those questions. I cannot like simultaneously just tell you all the answers to all your questions right here without taking exponential time. So then you can maybe start to see how it's not, the proof system doesn't get trivialized when the verifier can be random. So let me give you an example of a language, an interesting language, which has an interactive proof system like this, where you can become convinced statements like this, like a string is in the language, by having a conversation with an all-powerful prover, assuming the verifier is allowed randomness. And this you may have also seen before in 251, but we'll do it again. So this is not quite the language, but we're going to talk about this language, the language graph isomorphism. Okay, this is an extremely famous decision problem in computer science theory. It's a simple one. It's like the language of all pairs of undirected graphs, that are isomorphic. So I'll remind you what that means. Isomorphic means that there's some way to renumber the vertices of G prime so it becomes identical to G. In other words, like if you draw them but don't write labels on the vertices, they look the same. Okay? So as a decision problem, it's like you're given two graphs. You want to know, are they actually the same graph if you just rename the vertices? Okay, so for example, you should imagine that you're given these graphs in, I don't know, like adjacency matrix or list format or something. These two graphs are isomorphic. Maybe they don't look it, but like if you just call, let's see, probably if you call this one 4 and this one 3, if you swap these two names, then it'll become identical to this one. OK, but you see, I even had to think about it there for like 3 seconds. So if it's an n-vertex graph. It might take you a long time. And indeed, the naive algorithm is just try all n factorial different ways of permuting the names of, let's say, this one's vertices, and see if it becomes identical to this one. So what kind of proof systems could convince you of statements like some pair of graphs are isomorphic? Well, you don't need a very fancy proof system for this. This problem, this language is in NP. That should be pretty clear, right? I mean, if you have a pair of graphs and you want to know if they're isomorphic or not, like a prover could just tell you a way to renumber these vertices. That's like n log n bits of information, how to renumber these vertices. And then the verifier checks for itself that, indeed, once you renumber the vertices on this side in the way the prover suggested, they become identical graphs. OK, so that's easy. One question is actually whether or not this problem is in P. That's unknown. It's a very interesting question. Some people think it is. Some people think it isn't. For the longest time, it was known that you could do it in like something like 2 to the square root n time. And then in some big development from a couple years ago, a person called Babai got it down to like n to the polylog n time. So not n to a constant, but n to like log to the 11 or something. Which is kind of close to polynomial. On the other hand, I think he does not believe it's in P, even though he got it very close. Anyway, so it's an open question. If it turns out that it's in P, then you have a very simple proof system where there are 0 rounds of interaction. The verifier is just like, I got this. You don't need to tell me anything. I can check for myself if these graphs are isomorphic. But we don't know that one. OK, so why do I bring it up? I bring it up because of this problem, which is what we're going to really be interested in. I wrote the complement of graph isomorphism, graph non-isomorphism. OK, so this is, it can make a difference for these, NP things, like just if you switch the roles of yes and no, right? So this is, given two graphs, are they not isomorphic? And we can ask, OK, is this in NP? And it's a kind of familiar dilemma that we see when we think about, like SAT versus unsat, right? Like, it's not clear. Like, the way the whole problem is graph isomorphism is set up, it has like a very NP flavor to it, right? Like, two graphs are isomorphic if there exists a permutation that takes one of the vertices that takes one to the other. So that there exists is like very much of the flavor of NP, whereas the graph non-isomorphism problem, G and G prime are not isomorphic if and only if for all permutations of one set of vertices, like you don't get matching graphs. Okay, that has like a co-NP flavor. Of course, this immediately implies that graph non-isomorphism is in co-NP. But it's unclear if it's in NP, right? If I give you two graphs, and we want a proof system whereby you'll tell me something, and then I'll do a polynomial time check and become convinced that they're not isomorphic, it's not quite clear what to do. Like maybe the prover could say, hey, verifier, look at this vertex. It has degree 7, and there's no vertex of degree 7 in the other graph, so they're not isomorphic. Well, that might work sometimes, but it's not going to work for every graph. Also, the verifier didn't really need a prover for that. It could have just looked at all the degrees itself in polynomial time. So it's not clear. But as we'll see just now, it does have a very simple, in fact, interactive proof system. OK, so if I put up on the board two enormous 10,000 vertex graphs, and I claim to you these are not isomorphic, then by interaction, you can become convinced of my claim that there's no way to find an isomorphism between them, assuming you have randomness, which you do. OK, so let's see that. So this gives an example of a problem where we don't know it's in NP, but it does have one of these more liberal styles of proof systems. So you can become convinced of non-isomorphism. course, there's something a bit funny about it, right? Because maybe half of people think that actually graph isomorphism is in P. We just don't know how to prove it. In which case, graph non-isomorphism is also in P. So you don't even need any prover for it. But at least that's something we don't know if it's true or not right now. Whereas we know definitively that I can convince you that graphs are not isomorphic in the interactive proofs fashion. Any question? All right, so how are we going to do it? So like imagine here we are. We got G and G prime. It's in some, I don't know, adjacency list format. We're looking at them. And like I'm trying to convince you that they are not isomorphic. There's no way to renumber the vertices of G prime to turn it into G. So how's it going to go? What would convince you? Well, since you may have seen this before, I'll just spoil it for you. I'll tell you. So this is how the action goes. The verifier is going to flip a coin and thereby set a variable I to either 0 or 1, 50-50 each. Actually, let me change the names of these graphs to G0 and G1. And the verifier is going to send a 1-bit message to the P, just saying I. Oh, that's totally wrong. It's too early in the morning for me. It's much more sophisticated than that. That would be the worst possible thing for the verifier to do, actually. Right, let's reset. What does the verifier do? OK, so it secretly picks one of the two graphs. I is going to stand for 0 or 1. And it's going to, well, let's say it's going to let, I'll just write it over here, let H be randomly relabeled version of GI. OK, so it's going to use more randomness here. It's going to, having picked I, it'll choose one of these two graphs. It'll randomly permute the vertices by picking a random permutation. And it'll let H be the adjacency matrix format of the resulting graph. And then it's going to send over H. OK, that's much better. And what's implicitly going on, like the idea behind the proof system, is the verifier is asking the prover to guess whether H is a randomly relabeled version of G0 or of G1. In other words, to guess whether it flipped I equals 0 or I equals 1. OK, so in this proof system, the prover is obligated to send back a guess at I. And that's it. There's just two messages, this first graph, this single bit. And at this point, V will accept if P guessed, I'll put guess in quote, guessed correctly, and otherwise reject. You should really imagine yourself in the verifier's shoes. We've got these 10,000 vertex graphs, two of them up on the board. And like one of you just like secretly flips a coin, permutes the graph, and you write down a piece of paper, the randomly permuted graph, and show it to me. And I have to guess whether you randomly permuted G0 or randomly permuted G1. But you should imagine, I don't know if this is accurate, you should imagine that I have like unbounded computation time. I can think as much as I want. So why is this a good system? Well, let's think about these two conditions, although we won't exactly have these conditions because we have some randomness now. So there's always going to be a chance of error. But the verifier wants to become convinced with high probability. So let's imagine two cases. We'll start with the first case. Imagine that in some sense the claim is true. The claim being that these are non-isomorphic graphs. So let's imagine that this really is in the language. So these graphs are not isomorphic. Well, what that means is, when you choose either G0 or G1 and make a randomly relabeled version of GI, H will be isomorphic to exactly one of these two, right? H will be isomorphic to GI for whichever I you chose. And it won't be isomorphic to the other one, because we're assuming that G0 and G1 are not the same graph up to relabeling the vertices. So in this case, it will be isomorphic to exactly one of G0 or G1, namely to GI. Okay, and then if the prover has unbounded power or unbounded computation time, it can just try all the possibilities and figure out which one, G0 or G1, H is actually isomorphic to. Just try all the ways of relabeling H and see if it turns up to be equivalent to G0 or G1. So then the prover can figure this out and can figure out I with certainty. Okay, it'll definitely figure out I. And therefore, what we can finally say in this case is that the probability, and this is just over the verifier's random actions, that V accepts, it's actually 1. Okay. The verifier will definitely accept here. Okay, so that's good. Now, what about the other case? What about case 2 if it's not in the language? Okay, in other words, G0 is isomorphic to G1. So it's really G0 and G1 are just the same graph, relabeled. So now, when H is a randomly relabeled version of GI, it's equally well a random relabeling of G0 and of G1. So G0, G1, H is just a random relabeling of either G0 or G1. And so there's really nothing the prover can do. It could have literally equally well come from G0 or G1. From the prover's perspective, H is equally well be from G0 or G1. So information theoretically, there's nothing it can do. It can use randomness to guess, or it can just always output 0. What it'll find when it's doing any calculation is, well, H is indeed isomorphic to G0 and to G1. So it's basically stuck. There's no way it can tell which one you chose. So what you can conclude in this case is that, therefore, no matter what P's, let's say, strategy, no matter how it behaves, the probability that the verifier will accept is at most a half. In fact, it's exactly a half. It's literally no matter what the prover does, operates deterministically, guesses, doesn't matter. It's basically like you flip the coin and I have to guess it. Whatever I do will have probably half of success. Yep?
I thought the context of the prover is that regardless of whether it's in the language, he's trying to trick the verifier. So can't the prover I'm just going to ignore what you're saying, I'm just going to keep giving you 0, and you will get no information, or just 0, 1, 0, 1, 0, 1.
Well, you should imagine what the cheating, you should imagine I'll write the definition in a second, which will help. I'm trying to just do an example first here, but what you should imagine the prover should do when the claim is true, you should imagine that the prover is being helpful and is trying to give information that will help the verifier succeed. And when the claim is false, you should imagine a cheating prover who is just trying to trick the verifier into accepting. So it's not concerned about information per se. It's just trying to give the best possible answers to trick the verifier into accepting. And you can see here, it doesn't really matter what it's going to do. See, the verifier eventually only accepts if the prover guesses its coin flip. And the idea of this proof is when G0 and G1 are really isomorphic, the prover has literally no information about what the coin flip was. Because when it sees H, it's just has the same distribution as if the coin flip was 0 or 1. So really, it's reduced to the question of you flip a coin and I have to guess what it is. And therefore, no matter what strategy I use, like always say 0, or always say 1, or like flip a coin of my own to try to guess, like the probability it'll match your coin flip is a half. OK, so that's the analysis of this proof system. And again, as always, the proof system is sort of defined just by like the verifier's actions, like what it actually does and how it makes its check. And then you imagine what happens for like a helpful prover in the case where the string is in the language. And you imagine what happens for like the worst cheating prover when the string is not in the language. And this proof system is pretty good. So if it's in the language, you'll definitely accept. If it's not in the language, the probability you'll be accepting is a half. Okay, so this is a little bit like CoRP, one of the two. You don't want, it's not so great maybe that you accept half the time, even when the prover is cheating you. But just like in all randomized algorithms, you can repeat this system a few times, okay, and that drive this half down. Okay, so if you don't like this being a half, you can repeat this whole process 2 times, and the half goes down to a quarter. Okay, so what you'll do is you'll just play the whole game again. You flip a coin, send H to the prover will send back a guess, and you're like, well, I guess you were right this time, but like I'm going to try you again. So you'll flip another coin, send a new H over to the prover, it comes back with a guess. If it's wrong this time, then you can flat out reject. If it's right with this guess, you can say, well, maybe you got lucky, but if it's not in the language, it'd be a quarter chance that I got lucky twice. Okay, so you could repeat it 3 times, or you could repeat it n times, whatever n is, and the half would go down to something like exponentially small, like 2 to the n. So you can make n 100 or something. And after 100 rounds of this, if it guessed right 100 times in a row, they're probably not isomorphic, right? I mean, the chance that they're isomorphic is 2 to the minus 100. OK, and that's really good, right? I mean, except for this 2 to the minus 100 error, which is genuinely negligible, this proof system can really convince you about the truth of claims of this form. And that's pretty cool because we don't know whether or not this problem has like a standard proof, whether it's in NP. OK, so let me give a definition that formalizes this kind of proof system. OK, so this is yet another complexity class. So IP stands for interactive proofs, brackets K, is all the, I'm just going to write it in words, languages L that have a K-round interactive proof system, kind of like this, where if X is in the language, then there exists, a prover strategy such that probability that V accepts with the messages, and let's just make it like BPP. So let's say at least 2/3. Let's not get greedy and say that it has to be 1. And if X is not in the language, then no matter what, like a cheating prover says, let's say that the probability that the verifier accepts is less than 1/3. OK, so I guess we didn't literally on the first step show the graph non-isomorphism is in IP2 because we only got, this being 1 was good, this was only 1/2, it should be less than 1/3. So we could repeat it twice to get it down to 4. Okay. So for example, from what we just showed here, I suppose you would say that graph non-isomorphism is in IP 4. Okay? The exact constants here are not so important. But if you repeat this thing twice, you get the probabilities like 1 versus a quarter. OK, and if we are happy to allow some kind of unlimited number of communication rounds, as long as it's polynomial, then we get a class that's just called IP, which is basically you can have any polynomial number of rounds. And yeah, these people, Goldwasser, Macaulay, and Rakoff, like introduced this class, and they said, maybe we should consider this to be the class of all languages that have efficient proof systems, where statements of the form X is in this language can be proved, albeit in this interactive way with some small chance of error. And it became like an interesting question to understand this class. What can we prove? So we have some basic observations like NP is in IP. Okay, in fact, it's even in one round IP. Okay, because in NP, the prover just needs to send one message, and then actually the verifier achieves probability 1 here and probability 0 here. Okay, that's exactly the definition of IP. And we also cooked it up such that BPP is also in IP. In fact, it's even in IP0. This is a bit trivial. But since we allowed the verifier to be probabilistic, we kind of also capture probabilistic computation without proofs, right? I mean, IP0 is just like there really is no prover. The verifier just checks the statement, tries to check the statement itself, but we're allowing it randomness with 1/3 error probability. So this IP, therefore, is like an interesting class. I mean, we can draw these like pictures that we always draw. We have P here, and we have like NP contains it. We also have BPP, which I'm drawing it kind of big here, even though it's a bit misleading because maybe it just equals P. But as far as we know, it could be different from NP. OK, and now we found this interesting class of statements that you can have some kind of an efficient proof systems for, called IP. And it contains NP, and it contains BPP. And it also could contain some language that we don't know definitively is not in these is in either of these classes. Okay, so maybe graph non-isomorphism is outside both of these classes, but it does have efficient interactive proofs. So that's kind of interesting. On the other hand, like I did not draw co-NP here. Like we don't yet know the relationship there. Cool. So they invented that in the early 80s, and people, well, they were interested in it. They got interested in it actually for cryptography-based reasons, mainly. But it's still kind of an interesting philosophical question. Like, what are these languages? Because it's not just NP of things that have efficient proof systems. So we don't have so much time in this class. So I'm just going to tell you a bunch of things about IP. I'm now going to tell you many basic facts about IP. It's an interesting class. OK, we will not, unfortunately, prove any of these, but it'd be good to know. Let me just get a few basic things out of the way. So one thing is we allowed the verifier to be randomized. Maybe we should allow the prover to be randomized. Well, you can if you want, but it doesn't help in the sense that like it doesn't give you the ability to have proof systems for more languages. So let me just write this. Randomized provers don't help. And let me just say in words again what I mean by help. It doesn't enlarge the class of languages which have efficient proof systems in this framework. And the reason is somehow, from the prover's point of view, like using randomness is just sort of shooting itself in the foot. Like, I mean, if it had like a good system sort of on average for making the prover accept, like sort of an expectation over the prover's coin flips, like why wouldn't it just pick the best message for making the verifier accept, the one that like maximizes the probability of the verifier accepting? It may as well do that, right? We're not putting any bounds on the prover's power, so let it just like figure out like the best message it could have sent if it was planning on sending one of a random number of messages. OK, so that's a basic fact you might have been curious about. In fact, let's talk a little bit more about this from the prover's perspective. If it's thinking about like what message, let's say it's like in the middle of some proof or something or some proof system, like what message should it send in order to like maximize the verifier's probability of accepting in the end? Because actually, whether or not the statement is true, That's what the prover is always trying to do, like maximize the probability that the verifier will accept in the end. So in fact, let's say we fix some verifier v that the prover is going to interact with. Put yourself in the perspective of the prover here. And then we're given some x. OK, so in some sense, the actions of v define the proof system. Like what the verifier is going to do defines like what the proof system is. This is true even in the case of NP. And now let's say like the game begins. There's some x that they're both looking at, and they're trying to talk about. Let's imagine the task of computing the maximum over all prover strategies P of the probability that V sort of interacting with P accepts on X. OK, so put yourself in this mind frame. Like V is fixed. Now some X comes in, and you're the prover, and you're thinking to yourself, how should I answer V's messages? And this includes the fact that V is randomized. So I mean, it could ask you any number of questions. How should I answer its messages to maximize the probability that it'll accept? This is sort of what the prover has to figure out. But think of this as a computational task. Like V is a fixed Turing machine, and X is like an input string. And you have to figure out the best ways to answer messages. It's not too hard to see that you can solve this task in exponential time. You can pretty much just like write down like everything the verifier might do, and then just enumerate all messages you might send back to the verifier, and just that's exponential time. But like among all those things, like pick out the one that caused the highest probability of success for the verifier. In fact, if you work a bit harder, this is a common phenomenon, you can show you can do that in like a space reusing way, where you like don't write everything down, but like you reuse some space. So it turns out you can compute this using poly length of x space. OK, so I'm not going to prove that. Sipser, the textbook, proves that actually in gruesome detail, so you can look at that if you're interested. And this is a very interesting observation for a couple of reasons. First of all, it has two consequences. One consequence is that if L has an interactive proof system, then L is actually in PSPACE. In other words, I mean, what I'm literally saying here is IP is a subset of PSPACE. So why is that? So imagine you have some language L, and it does have an interactive proof system like this. And now imagine you're a PSPACE Turing machine, and you're trying to decide questions of the form, is a given x in L? Well, what you can do is run this algorithm, I mean, solve this problem in polynomial space. And in the end, you get out like a number, like the probability that the verifier would accept given like the best sequence of messages or the best message answering strategy of the prover. And then if that number is bigger than 2/3, you can accept. There is a way for the prover to make the verifier accept with probably at least 2/3. And if that number is less than 1/3, in fact, if that number is less than 2/3, if you think about it, then you can reject, because it means all prover strategies accept with probably at most 1/3. So that means if you grant yourself this much power, you can figure out like the situation with like what would happen with the best prover, and thereby decide if x is in the language or not. Yeah?
But I thought the prover needs to know whether, in that instance, the graph is isomorphic or not. So you're going to figure out the probability, and you already need to figure out if it's isomorphic or not. Why do you still need the probability? Can't you just return yes in the language or not?
Well, this is like specific to graph non-isomorphism. So I mean, what the prover, here we just know that there is some proof system defined by the actions of the verifier. And then we get some string x, and we're trying to, well, we're trying to just imagine we're the PSPACE machine now. We're trying to decide which of these two statements is true. We know that one of these two statements is true. Either there is a prover strategy, which makes the verifier accept with probably at least 2/3, or every prover strategy actually makes it accept with probably at most 1/3. So it suffices for us, the PSPACE machine, to try to figure out what is the success probability given by the best prover strategy. Now, in the graph isomorphism case, in the case where the two graphs are not isomorphic, then the best prover strategy will make the verifier accept with probability 1. And it's a sort of complicated strategy because, I mean, it involves like figuring out what graph this one is isomorphic to. But yeah, I mean, this is not completely trivial, but I mean, you have to prove, the verifier, sorry, the PSPACE machine will have to think for itself, like for every possible graph H that V might send over, what is the best guess for what I is? And that's what it does inside this computation. OK, so that's kind of nice in the sense that it puts some upper bound on this power of IP. It's inside PSPACE. OK. And another nice thing about this is it means that basically, without loss of generality, the prover can be modeled by a polyspace Turing machine. Okay, so in the definition of IP interactive proofs, we just said like you should imagine the prover as being like all powerful. It can do whatever it wants. It can do exponential time, double exponential time. Can solve the halting problem. Like it can do anything. It's really just like a function which takes in any message and like spits back a message. But what this shows is kind of nice. It says like you don't actually have to, in order to get the full power of IP, you don't have to really allow for like a magically omnipotent prover. It only needs to be as powerful as polynomial space. Because you just see like the prover can figure out the best messages to send back to the verifier to try to make it accept. With polynomial space computations. So that's a bit pleasant, like it's kind of reassuring. OK, we're running a little low on time, so let me say some more things. OK, let me just say a couple more things in words. Some surprising facts about IP. So notice here for graph isomorphism, we had like a nicer situation. We had one-sided error. When it's really in the language, the verifier always accepts. It turns out if you change this 2/3 to a 1, it doesn't change IP. And that's a non-trivial theorem. But what it means is if you ever have an interactive proof system for a language with two-sided error, you can automatically upgrade it to one with one-sided error, which is a little bit magical. Like that's not something you can do for a normal randomized computation like BPP. Just say like, two-sided error, I get rid of you. But IP is a cool class, so that's something that you can do. Another magical fact about IP is this. One thing we didn't talk about, or one thing that we used heavily in this graph non-isomorphism protocol, is that V's random coins were private. Like the prover doesn't, it's all powerful or whatever, but it doesn't get to look at what coins V used, right? The whole point was that like this I was a secret to P, and this relabeling was a secret to P. You can define a version of interactive proofs, IP, where the coins have to be public. So like the verifier is randomized, but like the prover gets to see all the coin flips the verifier made. And that would seem to really screw over the verifier, at least for this point of view of this proof system for graph isomorphism. But it turns out, in another like kind of miracle outcome, that also doesn't change the class IP. If you insist that the verifier has to show its random coins to the prover, it still does not decrease the set of languages that have interactive proofs. And that's also not very obvious. You could think about how you could get an interactive proof system for graph non-isomorphism where the verifier actually has to show all its coin flips to the prover. It's not too hard, but it's interesting. OK, so all these facts are nice. And in particular, they kind of tell you that IP is like a nice class. Like you change a little bit aspects of the definition, it's robust. It doesn't change the nature of the class. So people are pretty interested in this, well, somewhat interested in this class in the 80s. And they couldn't quite pin down what it was. But somehow at the time, the general feeling was that it was not much more than a randomized version of NP. So in the 80s, people thought IP, maybe not much more, they didn't know, but than some kind of randomized NP. OK, so it contains BPP. And it does contain some stuff which we don't know is an NP, but like, that was pretty much the main example they had. And one question you might have is, OK, is there anything else like surprisingly in IP, or is maybe that it? And maybe like the smallest thing inside PSPACE, or the simplest language inside PSPACE, which is not known to be in either of these classes, would be un3sat. It's kind of like the analog here. I give you like a 3CNF formula, and you're trying to have a proof system for proofs of claims like this language or this formula is not satisfiable. And people didn't really think that was possible. Indeed, in like 88, Fortnow, the well-known complexity theorist, and also Sipser, who wrote the textbook, conjectured that un3sat is not in NP, in IP. And it turned out they were wrong. So in 89, actually right at the end of 89, like December, Loon, Fortnow, Karloff, and Nissan showed that actually not 3sat, un3sat is an IP. So there is a way that we can have like an interactive proof to convince you that a formula is not satisfiable. Which is very, amazing, right? It's like contrary to the whole exists for all spirit of things, right? Like to convince you that a formula is satisfiable, no problem, right? I just tell you the satisfying assignment. How do I convince you that no string satisfies the formula in like polynomial time? Seems kind of amazing. In fact, they showed a stronger thing, which I'll talk about in a second, which is this problem called sharp 3sat. It's also in, I put it in quotation marks, IP. This is a problem of I give you a 3CNF formula, and it's not a decision problem. It's a function problem. Your task is to output the number of satisfying assignments, which it's 0 if it's unsatisfiable, greater than or equal to 1 if it's satisfiable. But they showed a proof system where I can convince you for like a given 3CNF formula that we're both staring at on the board exactly how many assignments out of the 2 to the n satisfy it. So I can convince you this formula has exactly 97 satisfying assignments. That's pretty amazing. In particular, that shows this because when it's true, I can convince you that the formula has 0 satisfying assignments. And then, like 2 weeks later, Shamir, I guess it was maybe in January, so it should be 90, show that TQBF is in IP. This is like the problem where you're given a formula of the form like there exists x1 such that for all x2, there exists x3 such that for all x4, et cetera, phi of x is satisfiable. And since this problem is complete for PSPACE, that implies that PSPACE is a subset of IP. And then we also know that IP is a subspace of PSPACE. So actually, this proved that IP equals PSPACE. So in fact, this was kind of a dramatic result, and it's considered like a very amazing result in complexity theory. Just IP and PSPACE are the same. In other words, the set of all languages that have an efficient proof system where you can efficiently prove statements of the form, this string is in that language, is actually a huge class. It's all the problems that can be solved in a polynomial space. So it includes unsat and all sorts of stuff. That's considered a big surprise at the time. It's still kind of surprising. OK, so in the last 20 minutes, I want to sketch. I don't have time to prove it, but I want to sketch this one. That you can convince a polynomial time verifier of exactly the number of satisfying assignments between 0 and 2 to the n of a given 3CNF formula. And actually, this proof is like not much harder. You know, he did it in like 2 weeks after seeing this proof. OK, so let's do a proof sketch of this claim. So let's imagine the setup. What's the task here? I'm the prover, you're the verifier, and we're both staring at some 3CNF on the board. OK, so maybe it looks like this, x1 or x3 or x9 bar, and x2 bar or x5 bar or x50. And OK, so like n variables, m clauses. OK, so we're both staring at some particular 3CNF like this. And what is the claim? The claim is that this has exactly k satisfying assignments. OK, so the input to this proof system is a 3CNF and a number k between 0 and 2 to the n. And like I'm trying to convince you of the claim that this formula has exactly k satisfying assignments. And what I'm going to tell you is I can do that for any value of k and any CNF formula. In particular, when the CNF formula has 0 satisfying assignments, I can convince you that it has 0 satisfying assignments. So I can convince you that formulas are unsatisfiable, for example. Or like this is even more powerful. OK, so the prover, me, and the verifier, you, are both staring at this. So how am I going to do this? What's very interesting about this is quite beautiful is that it uses an algebraic technique. Somehow it uses some algebra. So the first thing that we kind of both do in our heads is the following. We just say let q of x1 through xn be a certain polynomial. And I'll write it, and maybe you'll get the gist of what's going on. 1 minus x1, 1 minus x3, x9, times 1 minus x2 times x5 times 1 minus x50, times, OK. This has something to do with this. OK, so what's going on here? This is the polynomial. I mean, it's written in a slightly weird form, but it has n variables and adding and times and stuff. And it's cooked up such that if you plug in 0, 1 values for the variables, this thing is on input x in 0, 1 to the n. It's 1 if x satisfies the formula, and 0 otherwise. So why is that? You see, it's a big product of things, right? And let's take this clause, x1 or x3 or not x9. This piece here, if x1 is 0 and x3 is 0 and x9 is 1, so it's unsatisfied, then this will be 1 times 1 times 1. The whole thing will be 0, and that'll kill the whole expression. On the other hand, if you have any other of the 7 possibilities, then at least one of these three terms will become 0. So this whole bracket will become 1. So like it's like alive so far. Okay? And so this whole thing will either be 1 or 0. And it'll be 1 for a given x input if each one of these parentheses gets made 1, which happens if and only if each one of these clauses gets satisfied. Okay, so this is like some kind of polynomialization of the 3CNF. Okay, this is where the algebra comes in. And the kind of brilliance of the proof is that we're going to start talking about what happens when you plug in x values that are not 0 or 1. Somehow that's going to become relevant to the proof, which is kind of bizarre. Okay, so this is just kind of commentary. The prover and the verifier don't exactly write this down, but they kind of imagine it. Or one thing that's crucial is that they never try to like expand this out, like open up the brackets and expand, because there's two things here and two things here, and there's m clauses. So they would get like 2 to the m, like exponentially many terms and monomials and stuff. So they don't try to open it up, but they can sort of keep it in their minds like this. OK, so now, yeah. So I'm just going to talk you through an imaginary conversation between the verifier and prover about this exact claim, and hopefully you'll get the idea of how it's going. So the verifier sends the first message. This is like a speech bubble. Okay. And the verifier says the following. So you're saying that if I were to sum over all values b1 between 0 and 1, that's just two possibilities, 0 or 1, and over all values for b2 between 0 and 1, and over all values for bn between 0 and 1, of this queue of b1 through bn, I'd get k. Right? This claim is sort of the same as this claim, right? So this is like saying try out all the 0, 1 values of the b and compute whether it's satisfying or not, and you're supposed to get k. And the prover says, yeah, that's what I'm claiming. This is also just commentary. Actually, in the actual system, like no messages are sent yet. But this is just what they're both thinking. Okay? So it's just to convert the problem into something a little bit, an equivalent problem that's like more algebraic looking. Okay, so the verifier now is going to be quizzing the prover, trying to catch the prover in a lie, if the verifier can, about this claim marked star, rather than about the original claim in quotation marks. But they're equivalent. And it's a clever protocol. You wouldn't have just thought about it. So I'm just going to tell it to you, and we'll see why it works. Now, there's one other twist here, which, as I said, it's going to involve like plugging in numbers for the x's which are not 0 or 1. And again, since this actually has exponentially many terms, if you start plugging in numbers that are maybe large, the resulting numbers can become very large. And we want to make sure that every number we ever talk about is not too large. Should have at most polynomial in n bits. So we're going to accomplish that with a trick, which is another kind of gadget on this proof that, well, it's an interesting proof. So the next thing that the prover is going to say, and this is like a minor thing, but the prover will say it's important. By the way, here's a prime number, p of about, let's say, of 2n binary digits. So the prover is all powerful. I know this is supposed to be a little p. Sends over an extremely large prime number to the verifier. That'll come up later. So the verifier says, got it. OK, and there always is a prime number of about this many binary digits. And we now know that verifiers can check in polynomial time whether a number really is a prime. Of course, the verifier is always skeptical. Like maybe the prover is trying to send a non-prime here. Now that's based on 2000s knowledge, but even back in the olden days, 1989, we knew that primality was in NP. So in the olden days, the prover also had to send over a proof that this number was a prime. But nowadays, we're just like, don't have to worry about it. The verifier can check that for itself. OK. And let me make one more remark here. The verifier is trying to decide if this equation that I marked star is true. This gigantic sum of values of this polynomial equals this number k. And it's a little fact here that we're going to use, that this is true if and only if it's true mod p. And why is that? Well, the left-hand side counts the number of satisfying assignments of the formula. So it's a number between 0 and 2 to the n. But p, like the actual magnitude of p, is something like 2 to the 2n, which is way bigger than 2 to the n. So if you take a number between 0 and 2 to the n, mod 2 to the 2n, it's fine. Nothing happens. Okay, so this claim is true over the integers if and only if it's true mod p. And as a spoiler, I mean, this is getting a little more sophisticated, but we're going to use the fact that the integers mod p form a field. Hopefully you remember what that is. If you don't, it's not important because you'll live. OK. So now we come to the key part of the proof. Okay. Actually, let me pause. I mean, I know it's like quite unmotivated and weird so far, but it's crazy. Anything I can clarify right now? So so far in actuality, I mean, I have these speech bubbles, but actually the things that have actually literally been sent in the protocol is 2n bits describing p. And there's also been some computation, v, checked in polynomial time that p really is a prime. And all this other stuff is like things that they're thinking. OK, so here is the key brilliant move. Consider, and when I say consider, again, it's some things they're thinking about. I'm going to define another polynomial, which I'll call r. It has one variable, or maybe I'll call it an indeterminate, called capital X1. And it's this. What you do is you're going to look at Q, and you're going to plug in like just a symbol, x1, for the first coordinate. And you're going to plug in 0, 1 values for all the other coordinates. And you're going to sum over all possible 0, 1 values. Now let's study this object. This is a polynomial because, you took a polynomial and you plug some stuff into it, some numbers or some variables, so it's going to remain a polynomial. And it's actually only in one variable. So it's a univariate polynomial, like a high school polynomial, one variable polynomial. I also want to say that its degree is not that big. Its degree, well, it's at most the degree of q, because if you plug stuff into a polynomial, you cannot make the degree go up. And I should have said this before. The degree of q is at most 3m, right? Because each of these pieces has degree 3. And you multiply together m of them. And this is polynomial, by the way. That's not too bad, 3m. And so that's good. And I should add that we're going to consider this whole thing mod p. So its coefficients, are numbers mod p. OK, so its coefficients can be written down with 2n bits each. So it's a one variable polynomial. degree at most 3m, and its coefficients are between 0 and this 2 to the 2n. So you can write it, in principle, it can be written down with something like order mn bits. OK? So it's a very complicated thing. So the verifier maybe cannot compute it for itself. So it just asks the prover, what is this polynomial? And the prover, it's a poly-size representation. So the prover can do that. So the prover sends, like literally the good prover, sends over R1 of x1 explicitly. Sorry, R. Now the verifier is very untrusting of the prover, but it wants to believe that the prover is correct. And at this point, the verifier would like to check some things. First of all, the verifier checks, and this is related to the original claim, that R of 0 plus R of 1 equals k. Right? Because the original claim star is literally the same as saying if you plug in 0 for this, it's adding in the one more summation. If you plug in 0 for x and plug in 1 for x and add them up, you get k. OK, and this thing the verifier can do, because R is just an explicit poly-sized representation polynomial in one variable. So it can plug in 0. Actually, that's just taking the constant coefficient. Plug in 1. That's just adding up the coefficients. Add them up and check that it's k. And this is, I guess, all mod p if you like. But as we set up here, it doesn't really matter if you do it mod p or not. And if this doesn't hold, then the prover is like, well, either prover, you either sent me the wrong R, it wasn't true that the thing you sent me is this, or maybe your original claim was bogus. But anyway, I caught you. OK? So this makes the verifier happy. But the trickier thing is the verifier has to become convinced that the object that the prover sent it, let's call it actually R prime, because we're not sure if the prover is trying to cheat us or not. The object the prover sent us is really this polynomial that it's supposed to be. From the verifier's point of view, that's sort of the last thing to check. If the verifier could become convinced that this R prime that it got sent is actually what you got if you took the complicated Q and boiled it all down to this one variable polynomial, then the verifier would be like, OK, you got me. Your claim must have been true. OK, so we're almost done. We can do it in 2 minutes. So in some sense, the verifier has this kind of complicated object in its head, R, and has this explicit polynomial, R prime, and it wants to check that they're the same. And so this is what the verifier now continues to do. The verifier picks a random A in the integers mod p. And it sends A over to the prover. It basically says that, so, you must, if you haven't been lying to me, you must be claiming that this R prime that you sent me, R prime of A, when evaluated at A, equals what it's supposed to be. Q of A, B2, up to Bn. Basically, it's going to try to check that R prime equals R by evaluating both of them on a random input. And if they're different, there's going to be a good chance that it'll notice they're different because they'll have different values on this random input. And of course, the prover says, yep, that's what I'm claiming. And the point is, this is extremely similar to this. You have some specific number. This is just like a number the verifier can compute. And this basically looks the same thing as before. Like this is sort of a polynomial the verifier kind of implicitly knows, and you're trying to check that its big sum over all 0, 1 values is equal to an explicit number. And so the verifier can try to get convinced of this claim inductively by using the same system over and over, where actually it's going to put in a variable x2 here to make a univariate polynomial, and so forth and so on. And so that's, in some sense, the proof system. The verifier inductively uses the same scheme for this. And the last thing we have to check is whether this is good. So I mean, if the prover is telling the truth, then the verifier, all these claims will be true, and everything will check out. But if P was lying originally, so the original claim was wrong, then P is really in a tough spot. It can either send over the true R when it sends it over, but then this will fail, because if it's lying, that means the actual claim is false. So it sends over the true R, like the verifier will detect it here. So the only thing it can really do is send over a fake R. It has to send over an R prime of x1 that's different from the true R of x1. But if you have two, this is a basic fact that I don't really have time to elaborate on because I'm over time. But if you have two different degree 3m polynomials, they can agree on at most (3m) values of a. And the reason is the difference of these two polynomials is a degree 3m polynomial. And a degree 3m polynomial has at most 3m roots, at most 3m zeros, which means that there are at most 3m values of a which make the difference equal to 0. In other words, at most 3m values of a, which makes R prime of a equal to R of a. Like the verifier is picking an a between 0 and like 2 to the 2n or so. And this is like way, way bigger than 3m. So like it's extremely highly likely that when the verifier picks a random a, it's not going to be one of these like extreme lucky points where R prime equals R, whatever R prime was. And so if the P was lying originally, it'll send an R prime that's different from R. But then when the verifier picks an A, it'll probably be an A for which this equation is also false. And therefore, the prover will be like forced into lying again. And so like inductively, like the prover will always have to be like telling lies with extremely high probability unless the verifier picks an extremely unlucky A. And therefore, the verifier will eventually catch it in a lie up here. OK, I went way over time. Sorry about that. See you on Thursday.